All right, happy Friday, everybody. So today we're going to go through the last part of Intro Thermodynamics, is talking through first law, second law type parts, sort of briefing over to what will eventually become the second law next week. The quick reminder from last time. So again, if you remember back through, we've been talking through thermodynamics and discussing things. We've got a sort of new series of definitions that we want to make sure everybody's aligned with. So we first discussed states, right? A state function. Now, what was special about a state function? We talked about this concept. What makes a state function special, or what is the thing we define about a state? Change over time. Yeah, that's one part of it. That's more specific to a point. Yeah, extensive and intensive. Those are right. Those are state ones. If it isn't changing over time, that describes equilibrium. That's true, right? We usually have these equations of state where they are at this sort of equilibrium position. That's true. Yeah, the thing I was mainly gunning for, a special part about a state function, is they are path independent, right? We say, again, back to my water example, if I tell you something about this, let's say the density of this water, how this water came to be in this glass doesn't matter. It doesn't change the fact that the density in this state at this equilibrium position is a value. The temperature of this water is just a value. It doesn't matter if it was hot before and it cooled down and now at equilibrium. It could be cold and then warmed up. The value it is right now, as long as it's sitting in its equilibrium position, is what makes it special. It's a state function there. So path doesn't matter. That defines how we start. A state is a collection of these state variables that talk about energy, volume, descriptors, right? Path is how you get between two states. So we can now talk about these deltas, these initials and final. So if we go from one state to another, the path we get between them is what we describe, right? Now, last time we were talking pretty detailed about focusing on specific kinds of systems using ideal gases, right? We started talking about if we have an ideal gas, we have an equation of state for an ideal gas we like to use. What is that very famous equation for ideal gases? 5, yeah, PV equals nRT, right? And if we say that to simplify things, we're going to assume that this is usually going to be in a closed system, which means which of these values become constant automatically. Now, one is a constant to begin with, yeah. N becomes constant by saying it's closed. R is a constant because it is the gas constant. This leaves us our three handles, PV and T. And we can now go through different processes where if I manipulate or hold one of these things constant, it becomes really clear that there's this nice binary relationship. If I had pressure being held constant, volume and temperature are my only two sort of knobs, right? If I hold temperature constant, pressure and volume are my two knobs. And what's nice about this is having only two values, changing one has this equal or proportionality with the other. It makes it easy to do calculations. So this is going to be something we're going to focus on now. The other thing we discussed through was this idea, okay, if we have this overall process, we have an initial state that is at an equilibrium position, we're undergoing a change, and we have these two divisions, state functions, these are path independent, and our path variables. Now, we talked about two very important path variables for thermodynamics last time. What are they? What are their letters, or what do we call them? Work, yeah, and heat. That's right. Work is our W, heat is our Q. Remember, these are currency of energy. They're ways of sort of moving energy into or outside of a system. And generally, you can think of it, work is the physical stuff, right? That's using force over distance to either put energy into a system or get energy out. And then we've also got heat, which is the transfer of thermal energy. We call it thermal energy between different points. Now, again, I want to keep reinforcing this. If I add heat to a system, does the temperature have to change? It can change, but it does not have to change, right? We have ways of, if I add just this energy quantity I call heat, I can actually get out work, right? And this is what we described last time. If I add heat and get, for every unit of energy I add as heat, if I get that exact same value of energy out as work, what is that process usually called? It's this perfect transition where heat goes in, 1 unit of heat goes in, 1 unit of energy comes out as work, and in that process, temperature does not change. We call that, yeah, isothermal. The delta T is 0, and under that special case, it becomes really easy to understand this conversion of energy from either work to heat or heat to work. And when we did this, this is how we sort of framed the first law. The first law summarizes this and says all the energy in the universe is constant. In other words, it's conserved, right? If I undergo a change, initial to final, really what I'm doing is changing how the energy is distributed or where it's distributed, but I won't destroy it, right? We come up with this general concept that says all the energy in a system is our U or our E, the internal energy. And from that, I can actually move it between these things so I get a delta U or a delta E of a process. So in this case, as we discussed last time, if I was going to try and keep the temperature constant here, and then I know it's not what's written on this slide, but if the temperature was kept constant, I add heat, the volume is going to change. In this case, as we're showing with this animation. The average motion of our particles does not change. That's what we're sort of saying is our temperature part. This would be an isothermal process. Delta T is 0. The pressure and the volume are the only things that can change. If you see that the volume is expanding here, the internal pressure would have to go the other way. Volume goes up, which way does pressure have to go? If the volume is positive based on this relationship, yeah, the internal pressure would have to drop for this sort of to happen, right? This balanced it out. So, but this is how we can convert energy back and forth. This is the principle of using thermodynamics as for basically burning things to create motion in the sort of engines is what we sort of build this out of. So what we're going to talk about now is these cycles and how they relate to each other under what we call irreversible or reversible processes. So putting it all together, the reason we like to focus on these gases, remember before we said this quantity U, the internal energy inside a system, it is the measure of all of the energy distributed in any of the different sort of buckets, right? And do you remember, think back, does anybody remember there's like 5 different sort of general energies that we wrote out before? If I said U was the sum of all types of energy inside a system, yeah, there's translational, right? So translational moving, vibrational, that's the bonds are vibrating, yeah. Rotational, right? Spinning, electronic, and intermolecular. That's right. It's the entire sum of how these energies are sort of combined as chemicals in bonds, or how they're sort of held together as matter, and also how that matter is moving, right? A lot of those things, the first 3 we talk about, is just about particles and how they move around inside a system. Now, one of the really cool things about ideal gases, we assumed, do you remember the properties? We said ideal gases, there was a couple of points that we said had to be true to call this an ideal gas. Ideal gases, there's a couple of things that we absolutely made it, or what we define it as an ideal gas. Point particles, yeah, absolutely. There's no intermolecular interaction. They don't bounce around. There's no loss of energy, right? They bounce off everything else. Perfect galactic collisions, that's right. But it's that first point here, yeah, random motions. But it's that actually that first part here, that because we talk about this point particles, we're assuming that the gas, the atomic part of it, or the molecular part of the gas, is really simple to describe. In fact, in that case, if we assume an ideal gas is just a pinpoint, right, just an atom, no matter what the gas is, we're assuming it's a dot of matter, which most of its stuff we describe is all about its motion. It's about how it moves, how fast it's moving, and how it bumps into other things. That means we make this decision. We say ideal gases are the one system that I can just look at it and I could calculate the internal energy of that gas. Other systems, it becomes difficult to say how much energy, for example, is in this paper. Well, it's going to depend on how hot it is, how big it is, what that paper is made up, if it has moisture in it. It's complex, right? Really, what it's made up of is different ways of storing that energy, the bonds that are involved, right? Its density. For an ideal gas, we simplify it and say all of the energy in an ideal gas can be measured simply by understanding how those particles are moving. Which means we have this equation down here at the bottom. U, which is not delta U, I'm not saying change between. If I just say, here's a cylinder of an ideal gas, and I know how much there is, N, and I know what temperature it is at, T, I could say, well, the entire energy in this ideal gas is equal to blah. And there's 2 equations we typically use. There's the 3/2 nRT, and 5/2 nRT. The only difference between these two, so this comes down to the naming. Monatomic ideal gases versus diatomic ideal gases. What is an example of a monatomic ideal gas? Helium. Yeah. What else? Xenon. Yeah. What else? Argon. Gases, ideal gases that are made up of a single atom. So we have the noble gases, right? Helium, krypton, argon, xenon. They're the gases that are made up of a single atom. These are really truly ideal gases because they are just an atom. It is a point particle, which means all they can do is translational motion. They move around, right? So it's really easy to define their energy by saying 3/2 nRT. And again, for the full derivation of this, if you're interested, there's some great YouTube ones on this point. What we're really saying is physical particle of a monatomic gas is defined or can be measured just by how it moves in space. Diatomic gases, what is an example of a diatomic gas? Nitrogen, fluorine, yeah, hydrogen. Anything where there's O2, good example, yep. Why the equation gets slightly more difficult is a diatomic gas looks like a barbell, right? There's two atoms. It has this shape, which means there's not just translation, but rotation comes into it too. That's why the term gets a little more complex. We have this 5/2 term up front. So all it means is as long as you know that for these simple systems, a monatomic ideal gas, we can use the equation 3/2 nRT, and then we can look at it and say, look, as long as I know how much of that monatomic gas there is and its temperature, I can calculate how much energy must be contained in there. And again, this all comes down saying a particle can move around in this point, right? Diatomic gas, it's just 5/2. And again, that's just taking into the fact that some of the energy is going to be contained in rotational points. In a monatomic one, the rotational, it's a sphere. It cancels out. So the nice thing about this is back to this concept that the total internal energy is really just temperature related. This goes back to what we talked about last time. If we have a isothermal system, right? If I have something that we said is at pressure 1, volume 1, nRT, right? That's our initial state, and we're going to some final state where we have a new pressure and a new volume, nRT. And as long as we're in a closed system, this is a constant, R is just a constant, and as long as delta T is equal to 0, we can say that, okay, we can calculate this by P1 V1 must equal to P2 V2. All the energy is going to be contained in this either pressure and volume kind of relationship. So we had a special case where we're like, okay, you know what? If the delta T equals 0, that means something very specific about the delta E or the delta U for that process. Do you remember what we said there? 4 cases where delta T equals 0, the total change in internal energy of that system, not just constant, delta E for isothermal processes was equal to, it is 0. The total internal energy change for a system where the temperature does not change is equal to 0. Yes, and that's also true. Remember, for the general first law, we say delta E is equal to all the heat plus all the work in that process. The sum of the two path variables, heat and work, for a process will give us the delta E. For an isothermal process, this is how we look at it for a gas. It means that the pressure and volume as our descriptors here, that sum, Q plus W, is equal to 0. Another way of saying that is for isothermal processes, Q must equal W, right? That the heat and the work are antipodes to each other. If heat goes in and work comes out, they must be equal quantity, opposite sign for this equality to hold. And that's kind of contained here, right? We said, for example, in that piston example we just showed, if the volume goes down or up, that's the constant, or that's the part that's really talking about the work, right? Changes in volume are how we measure the work. So if a system was to add heat, but then do work, that's what we define for our signs of these two, right? Like this, if a system is, remember about this, what does the sign of Q, what's the sign of Q if we said the system gains heat? Sign of Q must be positive, right? What if I say the system does work on the surroundings? What is the sign of W? Yeah, negative. So what we're describing here is these isothermal processes where volume is changing and pressure sort of makes it up. Heat and work are balanced, equal magnitude, opposite sign. It's a way of interconverting between the two, okay? So now what we're going to talk through is sort of putting this to work in the context of an actual piston system. So we've got a series of these notes. These will all be posted up on there, but we're going to work through them on the iPad. So remember, before we defined a piston. What made a piston special is it was a rigid container. It had a lid, right? So it's closed. It's containing a gas. And because it's this rigid container, we can consider it a closed system. Which means for all the examples here, there is no change in N. Now, we also described in this system here, what we've got is a volume, and because there's a gas contained inside it, we can define sort of a pressure. This gives us some initial state. Now, we're going to consider first the expansion of this system. When we say expansion, that tells us something about a sign of volume. What is the sign for volume if we're undergoing an expansion? Yeah, volume has to be positive. So if this was going to undergo an expansion, we've got a larger volume here, volume 2, and volume 1, where under this expansion, volume 2 is greater than volume 1. Now, assuming if delta T is equal to 0, what can we say about pressure? This is pressure 1. Over here, we have pressure 2. Yeah, pressure has to go down. Under these systems, if delta T is equal to 0, that means pressure 2 is less than pressure 1, right? So we have this opposite behavior. Volume goes up, pressure must go down. And it's an expansion. Saying it's an expansion means that at the end, the volume must increase. So in order to do this, remember we talked about this before, these are our two states. There's a bunch of different paths, a bunch of different ways of going from state 1 to state 2. So we'll talk about a couple of different paths. What's first is what we're going to do is talk about an irreversible path. It's the way in which we're going to add or subtract heat to a system, and we're going to do it in such a way that this happens in what's called an irreversible way. Where we're going to describe this is actually in the context of a graph. So let me quickly redraw the two sort of visuals, right? So we've got piston 1, it's compressed, and our final, piston 2, is really, really big, right? Where there's this, here what happens is volume has gone up. It's a positive value, plus VE. What that means also is going between these two, pressure has gone down. It's a negative value. Okay. So if we're going to draw this, what I'm going to do is if I had a way of measuring on this axis, this is the pressure that I'm graphing, and over here on this axis, this is the volume in that system. I'm going to start off in this compressed state. In the compressed state, volume is small, so I'm going to say volume 1 is right here. It's some small volume right here. But at that time, the pressure is going to be high. So, sorry, I should go up. The volume is low, but pressure is high. This is our P1 state. At the end, we said that volume is going to increase, so the volume value is going to go up. We go to a larger value. This is our volume 2. Meanwhile, pressure is going to go down. we're going to end up at pressure 2 over here. So we can define these 2 points. If we were going to graph out just these two, sorry, let me do this shorthand. What I'm saying here is volume will increase and it will have a positive value. Sorry. My shorthand for this sometimes, plus VE means, means positive. I will try to keep it to only that. Minus VE, what I mean is negative. Apologize. Okay, so we begin to describe out this graph. We have our pressure 1, volume 1, and we're going to undergo an expansion, which means we have a larger volume, smaller pressure. And what I mean by path is, if you imagine this is now sort of 2 parts, since pressure and volume are the only things that can move, you can imagine doing this in some way. There's a bunch of different paths or lines that connect these 2 points, right? There's a bunch of different sort of versions we could go through. And what that means generally is you can imagine, since I have to move in these 2 like XY plane, the extreme example would be to only move on X and then only move on Y in this large step. We're going to call this the most irreversible one. In a practical world, think of it like this. The example that made sense to me is, imagine you start off, this is our initial state. And in that initial state, I have this massive, large block sitting on top of it. That is the pressure in that system. If it's sitting at equilibrium, I'm holding the lid of that cylinder down. And it's got this really, really big, heavy weight. So it's staying like this. If I instantly were to suddenly take this off, I lift that off, I relieve the pressure. The gas hasn't had chance, or energy has not had a chance to move at all. Imagine that pressure were to suddenly evaporate. It's just gone. If you think about that in terms of what's going on the graph, we start here at this high pressure. Instantly, the pressure drops here. The weight is gone. The pressure of the system does a transition where we suddenly drop the pressure of the system. Now, if we do that, the volume hasn't had a chance to come back to equilibrium. That is not an equilibrium state. It's now got no thing holding it back, but we still have the same volume that we started off with. So what happens next is, whoa, I can actually expand. I have no more thing holding me back. I am going to undergo an expansion where the volume will make up. So if you were to think about a movie like this, you imagine that the piston is initially completely compressed, the weight suddenly disappears, the pressure goes from P1 to P2, and then slowly the volume makes up or moves after. So you have this sort of binary motion of pressure moving first, and then the system catching up and the volume moving next. And it's just, this is the most extreme transition. Again, if you were to sketch this out, what we're really trying to graph on this pressure volume diagram is any line that connects these 2 points is a path. We just happen to be taking the most extreme path where it's all pressure changing and then all work changing. Okay, so it's a hypothetical construct. If we did that, look right here. This expansion, because we suddenly are at this pressure, it's an expansion at this pressure. So during the expansion, P is constant. The pressure suddenly changed, all the volume changes while the pressure is at that new point, right? What do we call a value? A change in volume at constant pressure is what? If we were to suddenly change the volume while the pressure is held, well, no, not isobaric. Yeah, sorry, the value here, we are changing this volume while the pressure is at that P2. This little rectangle down here is P delta V. And it's actually the P external, because remember, we removed that block. It now is experiencing the work, the pressure of whatever's left over, the atmosphere. So the external pressure minus the external pressure, delta V, this is our work value. So what I'm trying to sketch out here is this rectangle, this change in volume at this new P2 constant pressure, that is how much work this system will do. And we only focus on that because it's just the work component after we suddenly ablated or blew off this pressure. We can measure that, right? This is a measurable quantity that says that's how much work I got from expansion under these delta T conditions, or this is the expansion I'm getting under these sorts of conditions. And so this is the work that I'm getting that is due to expansion. So I'm going to call it W expansion. Okay, now we're at this final state. The reciprocal, the opposite version of this would be compression. So let's say we are now down here, and what I want to do is return. I want to go back up to this one over here. And we're going to use the same rules that we did the first time. For the expansion, I start with a system. I suddenly remove its weight. The whole system is experiencing this new pressure. Work happens after. This is the work the system does. This is the work the system is doing. The work the system is doing work on the surroundings, right? Because what we did is I removed the weight. The system is going to increase in volume. It will give off energy as work. Okay. If I have to go the other direction, this would be what? If I'm going backwards, what do I call that? Starting from a large volume and going to a small volume, this is called what? Yeah, compression. Okay, so let's draw that one out. This is going to be the example of now we're going to start at this end point and we're going to go back over. All right, so diagram. Our initial state now is this large state. We've got this large volume. I'm going to call it my V1. And it's at some pressure, P1. And I'm going to undergo compression back to a small volume, V2, P2. It's going the opposite way. So here, V2 is going to be smaller than V1. P2 must be greater than P1. The opposite applies. And if we were to graph out the same point, numerically, again, if we started exactly at those endpoints, so from the last graph, we had, wait a minute, what were my colors? Doop. Blue, okay. So I'm going to start over here. This is my P1 for the system. It's already undergone expansion, and we have our V1. It starts at a low, wait a minute, what did I do wrong? Doop. Ah, my axes are backwards. Doop, 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 sorry. Volume is down here. This is pressure. Okay, we start P1 over here, V1 over here. I'm just trying to draw this. This is in the same bottom corner that we left off at from the last time. After we've done the expansion, that was our end state. That end state is our new start state. We're going backwards. We're trying to reverse that process. So I'm starting at this point here, and I want to go back to a point up here. I want to go under higher pressure and smaller volume. And just like last time, the way we did this, the way we allowed this to happen is I have to suddenly change pressure to create a new initial or new pressure for that change. Volume catches up. So you're doing it in a sort of digital or a lateral way. Once again, if I'm starting over here, I'm going to suddenly change pressure. I instantly go up to this value. This is my pressure. During that time, pressure will stay constant, and I am going to undergo a change in volume due to that new pressure. And once again, that means I'm doing a change between these two different states. I have all this area down here. This is my pressure external times delta V, which is equal to my work. What's different about this work compared to the last one? What is different both qualitatively? Yeah, well, negative, right? It's going to be a different value. Work is going to have to go into the system. That's one. Second, yeah, what about size? Look at this rectangle compared to that rectangle. What can we...
Wait, excuse me.
Yeah.
Sorry, I have a question.
Yeah.
With the second graph, would your lines go all the way down to the x-axis, or would it only go to the starting volume? Like the starting pressure.
No.
Sorry,
Remember, it goes all the way down to 0. The area under the curve is the pressure times the change in volume. And what we're defining is, if the pressure is constant, it's the entire integrated area down to 0 under this point. Yeah, absolutely.
Okay, thank you.
Why is the net external pressure negative? Remember, this for a system, from the perspective of a system, we say that the system work is negative external pressure times delta V, where external pressure is just the quantity of force against that system, right? It's a measured value we can say is whatever that system is pushing against it. So external pressure, if it was a balloon, would just be the atmosphere. Here, we're dropping a brick on the top of it to do this compression. It's equal to however heavy, how much pressure that brick is exposing to the system. Yeah, for this example, what we're doing is taking, remember, we can move between these two, initial and final, any way we want. I'm showing you the first example where the path I'm choosing to choose, I completely change pressure and then I allow volume to change. It's the most rapid way I could move between these two, by doing an instantaneous change in pressure and then a change in volume. Higher system area because work is being done on the system. Yes, that sounds right. Like, remember, here you're starting from a small value to a large value versus the other way. We're going down. But in the end, yeah, the thing you can see visually here, if I were to draw these two guys side by side, so here's our first PV curve, here's our second PV curve. In the first case, we've still got these 2 points, right? Numerically, these are our 2 states we've defined. In the first example, we drop the pressure, then we move volume, leaving this value to be our work. It's the delta V that happened at this pressure, at this constant pressure. If we go the other way, start at blue, I change the pressure, I then allow the volume to change. This whole area under here is my work. It's the entire value under that curve. And what we notice here, the statement we can make, the work due to expansion does not equal the work due to compression. And I'll say that the absolute values, not just that one is negative and one is positive, the numerical quantities associated with these two are not the same. In fact, you will always see for this 2 point here, expansion will always be less. Oops. Not just does not equal. Expansion is always going to be less than compression. So now think about this for a second. Remember what we said before about paths. If I had a path between 2 different states, there's some paths, if I'm going to do that walking example we did from campus to the grocery store, there are some paths that do not expend very much energy, and there are some paths that expend a ton of energy here. In this case, we are focusing only on the work component, and in this example, if I rapidly compress the system or I rapidly expand the system, the work are not going to be equal to each other. Good question. Was about conservation. So remember, what did we say has to be conserved? Energy, not work, not heat. We're only looking at one of the 2 components. So based on this, we just said expansion work does not equal compression work. For this all to balance off enough not to blow up the universe, what has to make up that difference? Where is this extra energy we've created or destroyed? Heat. Heat was not shown on this graph. The point I'm trying to make is, if I have the same 2 points, blue and red, I can choose a path by which moving in a certain way is going to expend more work or take more work and then use less, or I get less back. That's between these two. So the work value is not equal. We call this an irreversible process because we're going to have to make up for this extra work value somewhere. We're going to need a heat value that's going to have to sort of play into this to make this thing balanced. This is not a case where this is a nice reversible system where all the energy is nicely accounted for within it in those sort of components. Here, if we do a rapid expansion or rapid compression, this just means that at these times, at this point over here, or this point over here, the system was not described by an equation of state. It's not in equilibrium then. At that point, we are sitting at some point way off of this point here. This is what graphically, this is what we describe as an irreversible process because, and the way we define it is the expansion work does not equal the compression work. In fact, the expansion work is going to be much, much, much less than the compression work because we did this single sort of change. Now there's a time constant that you can sort of think about this. This goes back to sort of the idea that we're using heat and work as a way of sort of moving between these two energy quantities. So let me again draw out our two states. So we've got our two graphs again. We've got our red state, our high state over here. And we've got our blue state, our end state over there. Or not end, sorry, the lower of the two states. Once again, if I were to choose to go, let's say the red state is our high pressure, low volume state, and the blue one describes the large volume, low pressure state. Which means going this way is known as expansion, and going this way is known as compression, right? We have the same two states. The direction defines what we're doing in terms of the change in volume between the two. Now last time, we did this as a single jump. We did a complete change in pressure. Then we had a change in volume. So once again, pressure, wait, I got it backwards again. I don't know why. Oh, no, I didn't. Woo-hoo. Pressure, volume, like this. For this time, I'm going to take a slightly different path. Instead of going to do a single jump, imagine we break up the change in pressure into two actions. So I'm going to do the first time. I'm going to take off half of the entire pressure first and allow the volume to catch up to create this intermediate state, and then take off the other half of the pressure and then let it catch up again. So instead of one big jump, I'm going to move between the red state and the blue state, now in two smaller changes in pressure. But once again, instantaneous change in pressure, follow up with volume. Instantaneous change in pressure, follow up in volume. Like before, because this is a single, because the delta V happens at that sort of constant pressure point, what we get is a nice unit equation for the work that happened here. It's divided now as these two rectangles instead of one smaller rectangle. And again, that's just because I sort of stop at this sort of intermediate state. It's like take a breath in between. If we do the other way, the compression, I'm again going to take one step halfway there, let volume catch up, and then halfway there, volume catch up. And once again, this defines the work. Now, if I was to put these guys on top of each other, do you think now does the absolute value for work, compression, does that equal the absolute value for work, expansion? No. Is it as bad as it was? Is the magnitude of the difference better or worse? Yeah, it's a little bit better. In fact, if you were to graph these things out, so again, I'm going to try and sketch this all on one graph. One big graph like this. Once again, red state, blue state. The first time we went down, over work. When we went back, up, over, all of this is the work. Only this top area, this is our difference. Right? This is common for both of the two. But this area up top here, not contained in that purple one, that's the amount of the difference between the work between those two different paths. Same thing. I'm trying to sketch it just over here. Start at red. If we go to blue, we're going to do it in 2 steps now. Step down, over, down, over. This is our work. Area under the curve. It's now broken into 2 rectangles. And the way back, we're going to go up to that same sort of half state here, and then up again, over, where all of this is the work the other way. What you'll notice is that the difference here is starting to get smaller. The principle we're trying to show, the more steps you take, the finer you divide this change in state between the two, the closer that these two processes will get to each other. You can do this one if you practice this out of, okay, 1 step, now we've got this whole part, right? This area here, we just saved this. That was part of the difference in energy between the two. But now that we're doing this, this exchange in 2 steps, this is never part of one of those 2 work processes. Yeah, this is graphical integral calculus. That is absolutely correct, Edison. Exactly. This is Riemann sums. That's all it is. The finer you take that stepping part, what you end up doing is actually get the true area under the integration. It gets close. I know. I just fooled you guys into doing calculus. Ha, ha, ha. Take that. I have a great weekend now. No, this is exactly it. So, but graphically, this is what happens. And we experience this in real life. What this kind of is saying, if I have 2 different states, and if I try to rapidly or try to do this in an exceptionally fast way, what happens is I have a lot of loss associated with that. But if I do this exceptionally slowly in little tiny pieces, now it gets closer and closer to a true value. In fact, if I was going to graph this out between these two, red state, blue state, and once again, instead of doing this, it's 2 steps, but I'm going to do this in an infinitely slow, perfect way. It actually forms a curve where this is our pressure and our volume. And the area under that curve here, if I was going to do expansion, this would be my area, which means if I ride this curve down this way, that's the work for expansion. And if I were to go up, the work from compression is exactly the same area. Under this case, this line is called the reversible path. And in that case, if we were to do this in this reversible way, that means that the work due to expansion equals the work due to compression. And the only way to do this thing physically is I need to move from this red state along this reversible path to the blue state, where at every time on this path I obey the most important part. The entire time along this path here, delta t is equal to 0 for every single instant of this transformation. We walk the path where the delta t never, ever, ever changes. In the first example, if I was to suddenly change the pressure and let the volume come up after, the system would be out of that equilibrium position. The temperature probably would have to sort of change because we've gone to this very, very far out of equilibrium state. We're not obeying the sort of, again, unit laws of ideal gases at that point. If we do this, we are obeying every part of it slowly as we go through it. We allow both the pressure and the 2 unit quantities of energy, work and heat, to work nicely in perfect parallel to each other. Think about it this way. As if I start up here at this high pressure, low volume at a red state. If I were to carefully, slowly lower the pressure on the system, I don't mean lower the pressure by like releasing gas, but if I were to lower the pressure on the system, in a normal equation, if I were to look at, let's say again, PV equals nRT, if I were to lower the pressure on the system and the volume here, think of this as like a spring, if the volume does not change fast enough, if volume does not change, what has to change in a closed system? Yeah, if the volume cannot change fast enough, the temperature has to change. But if I lower the pressure slow enough that the volume can always make up that difference, the volume can change here, temperature remains constant. That's the other reason that we call this reversible path is also known as the isothermal path. It's the path between these 2 points where the temperature always remains constant and we are obeying this rule. It just also means that it happens under that condition, work and expansion perfectly balance against each other. And it follows this sort of curve. Does anybody know what the equation of that curve should be? The black line? We'll jump into that one next one. But then again, if you were to integrate the function that describes those two, yeah, it has a 1 over x kind of form to it, exactly. Just remember what those two things are. Well, pressure equals 1 over v, right? That's basically what we're describing over here. Yeah, PV equals 1. Very good. Exactly, or constant. So it's what we're describing is these two different paths to move between these two. Under these two, okay, we're calling it the overall. We're still referring to this as isothermal expansion because the initial state and the final state still have this delta T equals 0 quantity. Remember, those are state variables. Temperature is a state variable. What we're describing now is how the path can change, and we have these two different kinds of paths. We have an irreversible path where you have at some point the pressure might change drastically, volume has to catch up, and as a result of that, that process is going to have different work and heat values as compared to, in this case, the completely reversible path. Heat and work are completely balanced the entire time. And think about it again, if we do this slowly, adding 1 unit of heat immediately comes out as 1 unit of work. And as long as we do that slowly, it's okay. If we were to suddenly ask the system to do a ton of work without giving it enough heat, the temperature would have to change. It's in this out of equilibrium type position. Okay. So I'm going to pause on that one. This is where we're going to wrap up today on this sort of concept. I want you guys to sort of look through this little part here, and we're going to go through and jump out on this part too. Okay? So, for anything else, again, I'm happy to hang out a little bit, talk through this little part. Have a look through the notes and sort of review on this. We're going to go through this one more time on Monday just to kind of solidify it. We're going to jump into our sort of week 3 sort of topics. Have a great weekend, guys.